All right, we're going to look at question 6, which is the question on equilibrium reactions. First question asks for one human activity that contributes to high nitrogen dioxide levels. You can choose any one from the following. Driving cars is probably the most common reason. Releases NO2, production of electricity, and more generally the burning of fossil fuels. So any one of those would be a good answer. 6.2, we're given this equilibrium reaction between NO2 and N2O4. It's one that we know well. First question asks us to define chemical equilibria, and this is something you just need to learn. It's the point at which the rate of the forward reaction equals the rate of the reverse reaction. And that's the definition for chemical equilibrium. All right, 6.2.2. This is now asking us to calculate the equilibrium constant. We're given the details there. And so we set up the table as you've been taught to do so. NO2 in one column, N2O4 in the other, and then ICE, the 3 rows, initial, change, and equilibrium. And I put little concentration brackets up in the top left corner to indicate that we're going to put concentration numbers in. You can, of course, also do it in moles and then change to concentration. So let's get going. The information that we do have is that 1.5 moles of NO2 is contained in a sealed in a 2dm cube container. So concentration is number of moles over volume. So 1.5 over 2 gives us 0.75. Then we're also told, we intimate that there is no N2O4, so it's 0 there. And then at equilibrium, we're told that there is a concentration of 0.2 moles per decimeter cubed of N2O4. So that's what we have. We now get to work on the change row. If we start with 0 N2O4 in equilibrium, we have 0.2, then that must have gone up by 0.2. And now we're working in the change row, and the important thing is to see that the mole ratio is 2 NO2 to 1 N2O4. And so twice as much NO2 will always react compared to N2O4. And so in the change row, we would put in there that there's a change of 0.4 because that's twice the 0.2, and that obviously decreases because it's a reactant, and so that's why there's minus 0.4. And that then allows us to work out 0.75 initial minus the 0.4 change leaves us with 0.35 moles per decimeter cubed of NO2 at equilibrium. We now have the equilibrium concentrations of NO2 and N2O4, which will allow us to do our calculation. So the expression for Kc is concentration of products over concentration of reactants raised to the power of the balancing number. We then fill in our values that we've just calculated in our table, 0.2 over 0.35 squared, and that gives us an answer of 1.63. All right, 6.3.1, we're now making a change to the setup, and the question says that the pressure of the gas increases. So that's a change, and we need to now work out how that's going to affect the concentration of NO2 at equilibrium. So having a look at the equation, we see that we have 2 moles of NO2 on the left and 1 mole of N2O4. So if we increase the pressure, the Chatelier says it's going to shift to decrease the pressure. So it's going to go to the side with fewer moles, which is the right-hand side. And so we favor the forward reaction. And because we favor the forward reaction, it means that the amount of NO2 would decrease. And so the correct answer there is decrease. Now I've gone through the explanation, but let's just quickly talk through it. We've got 2 moles of gas on the left, and we've got 1 mole on the right. And according to Le Chatelier, the equilibrium will shift to decrease the pressure. In other words, it will go to the side with fewer moles. And that's the side with N2O4. And therefore, the forward reaction is favored, and hence the concentration of NO2 decreases. All right, 6.4 is a bit of a tricky question. You need to work through the logic carefully. It says the temperature of the gas is increased, and when the equilibrium is re-established, the amount of N2O4 has decreased. Okay, so we increase the temperature, and that decreases the amount of N2O4. So if we increase the temperature, we know that we're going to favor the endothermic reaction. And because the amount of N2O4 decreased, we must have favored the reverse reaction, which is why the reverse reaction must be endothermic. And that allows us to conclude that the forward reaction must be exothermic, and hence delta H for the forward reaction is negative. So let's answer. Forward reaction is exothermic, and our reasoning is that an increase in the temperature always favors the endothermic reaction, and in this case the reverse reaction was favored because we decreased the amount of N2O4, and therefore the forward reaction must have been exothermic.